This video provides an overview of Chapter 3 as we look towards the final exam. Using this video, it's important to know what to study to authentically test yourself and transform instructional material. Knowing what to study, stoichiometry is included in Chapter 3, and then we use it again in Chapter 4 pertaining to solutions. We use it in Chapter 5 with thermochemical equations. We use it in Chapter 10 where we can apply PV equals nRT to reactions involving the stoichiometry of gases. So stoichiometry, an essential skill that we need because it touches on topics in multiple chapters. Authentically testing yourself, many of the questions within Chapter 3 we have numeric answers for. Did I do this correctly? Is this the correct answer? I'm sure those are things that come to mind. Within the e-text, I think the worked examples are a great resource to get feedback like that. Answers are then given for the follow-up practice questions. So when it comes to Chapter 3, I think the worked examples are a great way to get feedback and then subsequently authentically test yourself. It might be with practice questions, or if you look in the end of the chapter, the odd number questions there all have answers provided. When it comes to transforming the instructional material, I think you can probably summarize this entire chapter with 3 or 4 representative problems that you write down, show your thought process, include the answer, use that as a way to explain the idea. Within Chapter 3, here are the various learning objectives. The first one, balancing chemical equations. It's probably not a standalone skill. It's probably linked to other ideas. Predicting the products of simple combination, decomposition, and combustion reactions. The key one to know within that would be a combustion reaction. A representative question might be write and balance the combustion reaction involving the hydrocarbon propane gas. To do that, you have to know how to write a balanced equation. You have to know what the reactants are within a combustion reaction and what the products are. Calculating the formula weight and converting between grams and moles. I think that's a skill that you have. Here would be an example of calculations involving formula weights. Take a second, think about whether those are problems that are easy for you. This one's on the same topic, maybe a little bit more challenging. Calculating the percentage by mass of oxygen in the following compounds. I think the real heart of the chapter are these skills at the end. I showed the distribution here for how many questions I would anticipate. Most important is the bottom one where we have a balanced chemical equation and we're applying aspects of stoichiometry. Here are questions where we're converting between things like mass and the number of molecules present. Avogadro's number is relevant here. Look at this set. Look at them closely. Can you answer questions like these? Try to answer questions like these. Which ones are you confused by? When I look within the whole set, I think those 2 examples there might be the most representative. They combine multiple ideas. When I'm answering questions like this, I use dimensional analysis, or I'm careful with my proportions to make sense of the various relationships. Determine the empirical formula of the compounds with the following compositions by mass. Take a second. Do you have a plan to solve problems where you are seeking to determine the empirical formula? What's your approach? Here's the description within the textbook where we're going to assume those percentages apply for a 100-gram sample. We can then use the appropriate molar mass values and come up with an empirical formula. Here's a related question. This is asking for the empirical formula and the molecular formulas. Additional information is provided, such as the molar mass. Do you know how to use that information in order to go from the empirical formula to the molecular formula? Give that one a try. See if it works for you. These are in the category of combustion analysis. I think out of these 2, question A is a lot easier than question B. Question B states that the sample includes carbon, hydrogen, and oxygen. Why is it significant that the compound includes carbon, hydrogen, and oxygen, and the first one simply included carbon and hydrogen? How does that change your analysis? Here's the description within the textbook, how you can use the mass of the carbon dioxide produced to obtain the moles of carbon that were in the original sample, and the mass of H2O that's produced to determine moles of hydrogen in the original sample. With this information, you can come up with the empirical formula. It goes on to determine the mass of carbon in the original sample and the mass of hydrogen in the original sample. If you recall, that information is relevant for solving a question like B, because by difference, you need to determine the amount of oxygen that was present. These particular questions, these combustion analysis questions, I think they're easy to recognize, but you need to have a plan that works. To have success on these problems, I think you need to overlearn them with repetition. Don't simply look at this procedure and say, yeah, that will work. You'll get better with practice on these. You want to overlearn it, so as soon as you see this type of problem, you can quickly come to the answer. You don't want to stumble over it on a test and use up too much time and then end up simply guessing. At the end of chapter 3, those are where we have examples of a balanced chemical equation, and we're asked for different things. We might be asked to identify a limiting reactant, calculate the amount of product that's formed, consider the percent yield. When we were working on that before, we had two different approaches. We could use dimensional analysis, or I introduced BCA tables. Let me review some idea pertaining to a BCA table. So here we have a balanced chemical equation and information in mole amounts of what is present before the reaction occurs. Key step within this would be to determine the limiting reactant. Which one is limiting? With a BCA table, we can just pick one. So I'm going to say, what happens if I use up all of the O2? I will then look at the coefficients and use those to set up a proportion. The balanced chemical equation tells me that 2 moles of H2 react with every 1 mole of O2. So I'm just going to ask, well, if I used up all 7 of the O2, how much H2 would it take? That simple proportion tells me that I would use 14 moles. But I only started with 10. So I chose the wrong reactant to be limiting. I just used the other one then. So that's what I like within a BCA table. One feature, I can just quickly test that and determine which one is limiting. I will then use the proportions to come up with what's in the change line and fill in the rest of the table from there. Here's the same reaction but a different scenario. Take a second, read through that scenario. Can you take the details and use the BCA table to complete the problem? I see some specific information given here. It's describing, for example, that it's a sealed, empty container to start with. It's giving me information about after the reaction is complete, what remains in the container. It's using the term theoretical yield, and it's asking about what was initially added to the container. What information can you initially add to the table? This is what I think that I would initially add. Do you agree? Do you have questions on this point? From there, it's simply completing the rest of the table. I have information for the H2O gas where I did not have any initially present, but I have after the reaction what is present, so I can get a term in the change line. Once I have one term in the change line, I can use the coefficients to get the other ones, and it's easy to fill in the rest of the table from there. Anytime I have a scenario like this to keep track of what's going on, I use a BCA table. Dimensional analysis and BCA, they both work. They're both starting with a balanced equation, recognizing that moles combine with moles because particles combine with particles. And the coefficients in the balanced equation, they tell you the same thing. They tell you the proportions in which the reactants combine and the products are formed. We see different styles of questions, different features, but they all come back to the same skills. You may be asked about the limiting reactant, the amount of the excess reactant, it might be about the theoretical yield. Recall that the percent yield is the actual yield you got divided by, in theory, what you could have obtained. When you apply stoichiometry using the coefficients and the amounts, you're calculating the theoretical yield. Here's some representative problems for you. My suggestion, work through the numbers. Work through and reacquaint yourself with the skills that you have pertaining to stoichiometry. Here's another set where you're being asked to do something slightly different. This one right here where you're asked how many moles of the excess reactant remain after completion. For me, I'm using a BCA table within that because it helps me keep track of everything that's going on. That's one of the more challenging problems on a typical test, asking about how much of the excess reactant remains, especially when you have coefficients here that aren't simply ones and twos. A question here comparing actual yield with percentage yield. And then another set. Within this one, when it's asking how much of the various components are present, whether they're reactants or products, for me, I'm doing a BCA table because after I go through that, all my answers are apparent.